Hello and good morning to all of you. So, in this lecture, we will study some advanced topics related to stress. So, basically, what is stress and why do we need it? So, as you know that if we are going to apply a force on an object, okay, and it is this is external force that is being means applied over here. So what it will do, it will basically develop inside force inside the object, that is basically the reaction that is being developed over here. So if you want to calculate, means if you want to say that this much force is being applied over there, so it is not giving us any idea about the geometry of the object or cross section or area, that is this force is being applied upon this normal force. So that's why they coined this term stress basically. And what is the stress? Stress is intensity of this force that is being applied over this area. So in general terms, stress can be calculated by dividing force divided by the area of the cross section. Okay, but what is happening over here, guys? Sorry, that see here this point A and B. So what is happening over here, the deformation at A point and the deformation at B point, that won't be similar due to the properties, mechanical properties of the material, and also various impurities and all the things. So that's what is happening. The stress that is being acting on this area is not uniform. So due to this non-uniformity, what is happening there, that you cannot calculate or means define stress by constant area of the cross section. Means the stress is not constant, but it will be varying from A point to B point. Means at A point the stress will be maximum, but at the B point the value of stress will be different. So in this second example, you can see here that this body is being applied to sagging moment. So sagging moment, what is being what will happen inside the body? It will sag like this, and a reaction moment will develop inside the body at this cross section. Suppose at this cross section, so you can see over here at this A point and at this B point, the reaction, the stresses will be different. Okay, so at A point, since this is a compression zone, so this stress will be different. This will be compressive stress, and this is below the neutral axis, neutral zone. This is your, there will be extension in the body in at this bottom point B. So there will be tensile stresses. So you can see how the stresses are varying at a same cross section. So that is what is happening, that the stress is basically non-uniform quantity, and we have to calculate stress, value of stress, in order to design anything, okay, or any assembly or any body. So we have to calculate maximum stress value, so that we can know that how much material or what is the cross means the size of the cross section you have to give, so that it can withstand the particular yield stress. Okay, so we can see over here. So what Cauchy did, Cauchy was a scientist. What he did, he defined the stress in terms of a means in terms of a elemental stress. Means if you take a small element from the body, from this point at A, okay, and this element is being shown by a cuboidal element, and this cuboidal element has 6 faces. So we have as you can see in the figure, that we have 3 positive planes and 3 negative planes. So the stresses will be acting on each planes. Okay, so on each positive plane and each negative plane, there will be 3 stresses, 1 normal stress and 2 shear stresses. So in positive x plane and positive y plane and positive z plane, and also the same amount of same magnitude of stress will be acting on the negative x, negative y and negative z plane, so that the body should be remain in the equilibrium. Okay, So this is called as material element. Basically this is an infinitesimal element of size delta x, delta y, delta z, so that we can define the stress at a particular point in the body, continuum body, that what it is called basically. So this is basically the state of stress that was given by the Cauchy, and this is in three dimensions, so we call it as 3D state of stress. Okay, so how you denote the stress parameter over here? So as you can see that force is a vector quantity. It has only magnitude. You can define with it with magnitude and direction, and stress is basically your tensor quantity of rank 2, where force is rank 1 and stress is rank 2. It needs to define, or it can be defined with magnitude of the stress and direction of the stress, and also the plane associated with it, on which plane it is acting. Either it can be acting on means positive x plane, or positive y plane, or positive z plane. Okay, so here you can see the denotation. How can we denote stress? This is sigma ij, where I is the plane of stress always. When you are going to denote the stress, either it can be shear or normal, I first indices will be the plane of stress on which it is acting. So suppose this is the sigma xx, so this is positive x plane on which it is acting, and it is acting in x direction. Okay, this is y plane, and this is acting in y direction, and this is zz, sigma zz, so this is acting in z plane and it is acting in z direction, so that's why we call it as sigma zz. So now you can see here shear stresses. So each plane have two shear stresses. Okay, so this shear stress will act in y direction, and this shear stress will act in z direction, and in at y plane these are the two shear stress that are basically acting in complementary to each other. We will discuss that later also. So what they are doing is they are basically nullifying the effect of the rotation due to these shear stresses. Okay, so all these shear stresses will be acting on all the six faces, and these normal stresses will be acting on the all six faces of the element, so that they can nullify the action. Okay, so that's how you can show the amount of stress on a material element. So let's move further. So yes, so if our body is being basically the forces on the body is being applied in one plane only, so what we can do is we can neglect the stresses that are acting in z direction. Okay, or the normal and the shear stresses. So what we assume is sigma zz, sigma xz, sigma yz, sigma zy, sigma zx. Okay, zx will be 0. So that's what it is. So we can neglect those because there is no force is acting in z direction, and this 3D state of stress that we have learned in here, this 3D state of stress. Okay, this can be reduced to two-dimensional state of stress, 2D state of stress. So what we have here, this is your plane, this is your a plane, suppose this is our coordinate axis xy. So this is your plane on which sigma xx is acting, and what the thickness of this element, what we take it as 1 unity. Okay, so you can see over here where we have collected this stress at this a point, the normal stress is acting and a shear force, normal force is acting and a shear force is acting, and this material element that we have taken from here of the means sigma x by sigma y size, and the thickness of this element is unity 1. So and we neglected all the stresses that are acting in z direction. Okay, so yeah, so that's thing basically. So there's one normal stress is acting on this positive x plane, one shear stress is acting on positive x plane along the cross section, and this is perpendicular cross section, and here also. So in negative x plane we can see that there is sigma xx dash and tau xy dash, and this is also 0. So what are these? Basically tau yx and tau y dash x, these are basically acting on positive plane, and this is also acting on positive plane, and this is on the negative plane. So if we apply equilibrium equation over here, we can directly see that sigma fx is equal to 0, this will give you sigma xx is equal to sigma xx dash. So that this magnitude of this stress is similar, but the direction will be different, opposite direction, so that there should be an equilibrium. And sigma fy also, you can see here that this basically on shear stresses are acting in this positive and positive y plane will be equal. Okay, now what we have to do is we can calculate the amount of moment that is being applied due to these shear stresses about at this point A. So what we are going to try to do is we are trying to see whether this tau xy and tau yx are equal or not. Okay, so we can see the moment, and we can just first of all what we have to do is we have to convert these stress in terms of area. So tau xy into this delta y into 1. Okay, and one moment will be tau yx into delta x into 1. So what it leads to, tau yx dash is equal to yes, tau yx dash is equal to tau xy, means that this tau yx and tau xy will be equal. Okay, so this is called as a complementary property of the shear stresses. So that's what they are doing is, since there is one shear force acting over here at this phase, and what is happening, so that this body should not rotate, there must be a equal and opposite shear stress will be acting on this face also, so that body cannot rotate, and on positive and negative planes also there will be a complementary shear stresses. Okay, so this is how we can show the two-dimensional state of stress. This material element is acting, and suppose sigma yb was also acting due to Poisson's effect or something else, or some other load is there. So the normal stress is how we can denote it as sigma xx, sigma yy, and also I have just basically split these. You can show this with the same diagram. Okay, so due to means for the for the sake of usability. Okay, to make it easy, so this 2D state of stress is being basically, all the shear stresses are being applied over here. So tau xy, tau yx, and this is tau y and tau xy. So why I have shown this same, you can show with the same value also, tau xy, tau xy, tau xy, because all the values are similar but the direction will be equal. And also how to see, means all what we assume is, we always assume that there will be a tensile stress are acting, means tensile stress that is being acting outwards at the planes. This is the plane, and this is also the plane, and this is also a plane, and this is also a plane. Okay, so this is positive x plane, and this is positive y plane, and this is positive x plane, and this is positive y plane. So shear stresses are acting in positive direction, and shear stresses are acting in this direction, positive x direction, positive y direction. So this is how we can denote the shear stresses. So this arrow means the positive and negative will totally depend upon the shear force. Okay, since see here it is downward, the shear stress will be downward. Okay, and the normal stress, suppose this stress was compressive stress, so what we have to see is there will be means arrow will be inwards, not outwards. Okay, so that's what is happening over here. So this is how you can denote two-dimensional state of stress. Okay, so in next lecture means in next topic we will see different thing. Let's move to that. So this is basically how we can calculate the change in volume, and also how we can calculate the means strain in the body when the body is being subjected to all three stresses, normal stresses. Okay, so if a body is subjected to only normal stresses, there only will be change in the volume, and if a body is subjected to shear stresses, there will be change in shape of the body. So for the volume dilatation, this is also called change in volume, is also called volume dilatation, and this is how we can calculate the total change in volume or volumetric strain you want to say. Okay, and after that we will derive relationship of this modulus of elasticity in terms of modulus of rigidity, and in terms of modulus of modulus of in terms of Young's modulus. Okay, so what is basically going on here, this body is being subjected to three normal stresses, three normal tensile stresses, and this phase is positive x phase is being applied by sigma x-axis, and this is sigma yy, this is sigma zz, and you can see over here what is happening here, guys, that due to Poisson's effect, means when this stress is being applied over here on this positive phase, and same and similar amount of stress being applied on negative x positive x phase, and this minus sigma xx will be applied over here is negative x, okay, phase. So what is happening here, that this will be elongating this body in x direction. Okay, then due to this there will be elongation in the body due to this stress in x direction, that is being acting in this x direction, and this is acting along the, means elongation will be in x direction. So what is happening due to Poisson's effect, since this is elongating in x direction, this in y direction and in z direction there will be a contraction. Okay, so the total amount of strain, that is we are going to calculate longitudinal strain and lateral strain. So longitudinal strain, how we can calculate total amount of longitudinal strain is that due to this shear stress, normal stress, what in what direction what strains are there. So I have just summarized over here that due to sigma xx, what we have is longitudinal strain in x direction and lateral strain in y and z direction due to Poisson's effect. Okay, and this is sigma y due to this stress in y direction, there will be longitudinal strain in y direction and lateral strain in x and z direction. Okay, and similarly for sigma zz. So what is happening here, guys, that if we want to calculate total amount of strain in x direction, so we have to take care of the strain that is being calculated in longitudinal axis. Okay, means in this x direction, and also in this x direction also there is a lateral strain caused by this sigma yy and sigma zz. You can see over here sigma yy is causing lateral strain in x direction, and sigma zz is also causing lateral strain in z direction. So we can calculate the value of lateral strain by using Poisson's ratio, and we can calculate the value of longitudinal strain by using sigma upon E, like this. Okay, so these are the relations. So what we have done is we have just put the values of longitudinal strain and lateral strain. Okay, so this is since we are calculating in x direction, total strain in x direction, so this will be longitudinal strain, and this will be lateral strain, and this will be lateral strain. Okay, and in y direction, so there will be one longitudinal strain and two lateral strains due to other stresses. Okay, and in z direction, one longitudinal strain in z direction and two lateral strain in x direction and y direction due to stresses x, sigma xx and sigma yy. Okay, so what is this? Basically these are the various elements, total strain that is being calculated in each direction, x, y and z. Okay, now so how we can calculate total volumetric strain? Just adding them. So total volumetric strain is given by epsilon xx, epsilon vx, epsilon vy and epsilon vz. So that is how we can calculate, and we just sum it up and we can take the commons, and this is the relation that you get. So this is the thing. So how it is being related to bulk modulus of elasticity. So what is going on here, you can see here the original length of the element was sigma x, sigma y, sigma z, and now the change length is this. Okay, so this is the change in the x direction, y direction, and change in the z direction of the body. So what is this? Basically this we can rewrite it as this delta x can be rewritten as, and this new or current means dimension of the body can be written it as like this: 1 plus epsilon x. Epsilon x is basically the total strain in x direction, so it is basically the same, epsilon vx or epsilon x over here. Okay, so this is delta y and delta z. So delta x dash, delta y dash, and delta z dash are the current change dimension of the body, okay, after the application of the load. And delta x, delta y, and delta z are the original dimension. Okay, so what was the original volume of the body? Volume will be given by just multiplying all the three. And what is the current volume? This is the current volume. So just multiplying all these equations. So what we get over here is basically that after multiplication what we have here is this. Okay, this is we can means put all these value of the equations over here like this. Okay, from here delta x dash, these equations, let's put them here. And what is the change in volume? Change in volume will be current volume minus the original volume. So this is your current volume and this is your original volume. Just multiplying it and opening the brackets, what we have here is with one term, this is sigma delta x, delta y, delta z, plus bracket epsilon x, epsilon y, and epsilon z, and then bracket closed, and we have just common sigma x, sigma y. And try to yourself, it is very easy. And these are the higher terms, basically these will be the very small term that we can neglect, and minus the original volume. So after subtracting it, what we get it is change in volume will be equal to this, and or this is volumetric strain, that is basically change in volume is getting to this. Okay, and also what we know over here is that what we know is we know that change in volume will be equal to this expression is equal to this expression. Okay, this expression. So this expression we can just put the values from this volumetric strain over here, and just what we do is we just evaluate these, means equate these terms. And what we know here, if our all the stresses have same value like sigma, okay, like hydrostatic pressure, so the at the bottom of the sea, or at the means if the body is in the water, so the stresses will be acting means all the stress in all the direction will be similar. Okay, so this is sigma, the sigma axis, sigma y by sigma z, z is equal to sigma. So just put the values and calculate it, and what we get it as like this. Okay, and what we know is also that volumetric strain stress is directly proportional to volumetric strain, and that constant is basically your bulk modulus of elasticity. And just equating these terms, what we get it here is k is equal to E upon 3 1 minus 2 nu, and nu is your Poisson's ratio. So this is how you can calculate or derive this relationship, and also the change in volume also. And this is how you can calculate the total amount of strain acting in the body, okay, at in different directions. So you have to take care of that. What you have to take care that how you are going to calculate means what are the various strains that are being you have to add basically. So this will be longitudinal strain, this is lateral strain, and this is lateral strain. So in each expression there will be one longitudinal strain, one lateral strain, sorry, two lateral strains. Okay, so in each directions we have all these. So just do some examples, okay, from the book or internet, and this will be good to go. So next lecture we will see the stress transformation. Okay, so thank you.